Okay, so the next exercise that we have here is you want to find the limit of tan 2x by x minus pi by 2 as x tends to pi by 2. So if I evaluate this function at x is equal to pi by 2, what I will get is basically tan of basically 2x would be 2 times pi by 2, which is equal to pi, and pi minus pi by 2 is equal to 0. Now tan pi is equal to sine pi by cos pi. Now sine pi is equal to 0, so 0 divided by anything is equal to 0, so this becomes 0, so you'll get 0 by 0. Now since you get this in 0 by 0, 0 divided by 0, you will have to, you'll have to basically find the factor that is causing the numerator and denominator to go to 0. Eliminate them, and then you will be able to find the limit of the function at when x tends to pi by 2. So then what you can do is that you can write, I mean, of course it's not very straightforward. I mean, normally you would not see this. I mean, I did not see this, but as it turns out, if you take x minus pi by 2, if you take this as y, then basically tan of 2x is going to be equal to tan of, then based on this, x becomes y plus pi by 2. Y plus pi by 2, x is equal to y plus pi by 2. Then tan of 2x would be tan of 2 times y plus pi by 2, which is equal to tan of 2y plus pi. So tan of this angle, and you know that tan of 2y plus pi, you need to know what that is. So basically, you know that tan of x plus y is equal to tan x plus tan y, and 1 minus tan x tan y. So then based on this formula, you know, then you can write tan of 2y plus pi is equal to tan of 2y plus tan pi over 1 minus tan of 2y tan of pi. So basically tan of pi is equal to 0. So this part is 0. And again tan pi is 0, so this whole thing becomes 0. So then what remains here is tan of 2y. So tan of 2y plus pi is equal to tan of 2y. Okay, so I kind of got into trigonometry, but then I had to go back because this is this is not a good place for trigonometry, really. And that I suppose it's enough to note that basically tan of 2y plus pi is equal to tan of 2y, and that's enough for now. So now I can rewrite this limit as the limit of basically tan of 2x is tan of 2y in this case. So I can write this as tan of 2y, and x minus pi pi by 2, I can write it as y now if x minus pi by 2 is equal to y, now when x tends to pi by 2, then y tends to 0. X tends to 0. So that is that. Now as you can see, tan of 0 is equal to 0. When if I evaluate this limit as evaluate this function as x tends to 0, then tan of 2y, which is tan of 0 degrees, is equal to sine 0 by cos 0. So sine 0 is equal to 0. So tan of 0 is equal to 0, and then you would get again 0 by 0. So what I can do is that I can write this as the limit of sine 2y by cos 2y over y as y tends to 0. And then I can write this as the limit of sine 2y over y times cos 2y as y tends to 0 and so what that means is that I can write this as the limit of sine 2y to y. I can write this as sine 2y to divided by y times 1 over cos 2y. And then as you remember, hopefully, we said that the limit of sine x by x as x tends to 0 is equal to 1. Now if I make this a 2y and then multiply a 2 over here to basically cancel these two 2's out, and then as x tends to 0, what happens is that I can write this as the limit of, well, this is of course a constant, I can take it out. The constant 2, I can take it out. 2 times the limit of basically sine 2y over 2y as y tends to 0 times the limit of 1 over cos 2y as y tends to 0. Well, of course, as y tends to 0, of course 2y tends to 0 because of course this is a y. Well, you see over here, as y tends to 0, of course, as y tends to 0, 2y tends to 0. So this is going to be basically a 1. So this is going to be 2 times 1 times, and the limit of 1 over cos 2y as y tends to 0. As y tends to 0, basically 2y tends to 0. and cos of 0 is equal to basically 1. So 1 over 1 is equal to 1. So this is equal to 2. So that's basically, that was question number 22. That was question number 22. Number 23, you want to find the limit of f of x. You want to find the limit of f of x as x tends to 0 and the limit of f of x as x tends to 1, where f of x is equal to this function 2x plus 3 for x less than or equal to 0, or 3 times x plus 1 as x greater than 0. Okay, so this function is x tends to 0. Well, this is a little bit trouble, this limit, because I think you have to do it manually. There is no way to do it. There is no way to use any formulas here, because the function is kind of ripped apart, you know. And what that means is that we need to basically the limit of f of x as x tends to 0 at x is equal to 0. You see the function is basically something like this. It is 2x plus 3, so 1, 2, and 3. And 2x plus 3 would be it would be aligned with slope 2, so so this point over here, this would be one point, and then this would be another point on the graph of this of the function. Would be a something like this basically, and this is for x less than or equal to 0. Less than or equal to 0, so that means that this point is defined for the function x is equal to 0 is defined, and so the x for x is greater than 0, this point is this part of the function is not defined for x is greater than 0. For x is greater than 0, you have 3x plus 3. 3x plus 3. So 3x plus 3 would be basically again the same point, but then the slope of the function changes, meaning that the slope of the function is going to be 3, meaning that you would get this point over here, and then the function does something like this. You see over here the slope of the function, this part of the function is different from the slope of this part of the function. And the problem here is that you basically, when x tends to basically in this case, the limit of f of x when x tends to 0 from the right, for example, should be evaluated based on this function, because this is for x is greater than 0. And so if I set x is equal to 0 here, I would get a 1. I would get a 1 because 3 times 0 is equal to 0, and then the value of this function at very, very close to 0 is going to be equal to, so let's suppose that the function is f of x is equal to 3x plus 3. Now f of 0 here is going to be 3 actually, not 1 but 3. It's going to be 3. Now you see that basically the limit of f of x when x tends to 0 from the left should be decided based on this part of the function, which is basically this part. So let's suppose that f of x is equal to 2x plus 3. And so even though the function is kind of ripped apart at this point, I mean, it kind of changes the slope, the limit still exists at this point, because you see over here f of 0 is equal to 0 plus 3, which is equal to 3. Excuse me. Is equal to 3. And so this is equal to 3. So then you can say that the limit of f of x when x tends to 0 from the right is equal to the limit of f of x when x tends to 0 from the left is equal to 3. And also the value of the function at 0, f of 0, is equal to basically 3 again. This is actually equal to the value of the function at x is equal to 0. This is equal to f of 0. So that is that. Now what happens if you want to evaluate the limit of this function at when x tends to 1? If you want to find the limit of f of x when x tends to 1, you just simply evaluate the function at x is equal to 1, and that would be basically f of 1, and f of 1 has to be evaluated based on this part of the function, which is basically using this part, 3x plus 3. Assuming that f of x is equal to 3x plus 3, then when f of 1 over here is equal to 3 times 1 plus 3, which is plus 3, which is equal to 6 basically, which is equal to 6. So that is basically the limit of this function at these 2 points. So let me check my answer. 23, 3 and 6. Yes, 3 and 6. So that is that. Now 24. Okay, so now suppose that you want to find the limit of f of x when x tends to 1, where f of x is equal to x squared minus 1 for x less than or equal to 1, I'm sorry, and negative x squared negative 1 for x greater than 1. So you see that this function is basically the value of your function at 1 is given by this basically this what do you call it, by this clause. This is called the clause. This part over here, this is called a clause. This is also called a clause. So basically, if I want to find the limit of f of x when x tends to 1, I have to get, as you know, I have to get close to 1, very close to 1 from the right and from the left. So the limit of f of x when x tends to 1 from the right, for example, is equal to the limit of getting close to 1 from the right. That has to be done using this clause over here, which is for x is greater than 1. So the limit of negative x squared negative 1 as x tends to 1 from the right, which is basically the same thing as finding the value of this function at x is equal to 1, which is equal to negative 1 squared minus 1, which is equal to negative 1 minus 1, which is equal to negative 2. And the limit of f of x as x tends to 1 from the left is equal to the limit of from the left you have to go for x is less than 1, which is basically this clause over here, x squared negative minus 1 as x tends to 1 from the left, which is the value of this function at x is equal to 1. So 1 squared minus 1, which is equal to 0. So as you can see, the limit of f of x as x tends to 1 from the right is not equal to the limit of f of x as x tends to 1 from the left. And so you can say that the limit of f of x as x tends to 1 does not exist. And this function is basically defined at x is equal to 1. The value of f of x at x is equal to 1 is f of 1, which you can calculate using this clause over here, which is basically 1 squared minus 1, which is equal to 0. So the function is actually defined at x is equal to 1. But the limit of the function at x is equal to 1 does not exist. Well, if you want to see a graph of this function, we said that f of x is equal to basically these two clauses, x squared minus 1 for x less than or equal to 1, and negative x squared minus 1 for x greater than 1. So then you have basically for basically x squared minus 1 is basically x squared minus 1 is basically this function over here. X squared minus 1 would be, well, if you want to know how to graph these functions without doing much calculation, you see f of x is equal to x squared is some function like this. You already know this. So this is f of x is equal to x squared. Now if you have f of x is equal to x squared minus 1, it's going to be some function like this. It is basically a function that it's a parabola whose vertex is basically shifted down by 1 unit. This is 1 unit. The vertex is shifted down by 1 unit. Shifted down by 1 unit. -1 shifted down. Now if you have, so this is about x squared. This function over here is f of x is equal to x squared minus 1. Now this function over here, now if you want to graph negative x squared minus 1, now to basically this parabola is basically f of x is equal to negative x squared, and of course you can compare this function to this function. You see that it's opening upwards, this is opening downwards. So f of x is equal to negative x squared is this function. Now if you shift this function down 1 unit, if you shift this function down 1 unit, you will get to this function. Meaning that if I draw this function over here, and if this is 1 unit, then this function over here is basically f of x is equal to negative x squared minus 1. Okay, so this is about these two functions. Now, coming back to the function that we had, f of x is equal to x squared minus 1. X squared minus 1 would be this function over here, 1, comma 1, so you would get this point over here, and 2, comma 4 would be 1, 2, 3, and 4, so this point over here, and this point over here, so your function would go through these 2 points over here. Okay, so that would be your function. This would be f of x is equal to x squared minus 1. But this is only for x's less than or equal to 1. Meaning that less than or equal to 1, meaning that for x greater than 1, this clause is not relevant anymore. So I can simply erase this part. And then for this part over here, you can see that the function is negative x squared minus 1. So it's going to be this function over here, and then this is only for x is greater than 1, meaning that for basically starting from this point, x is equal to 1, and then it goes down like this, meaning that these parts are not a part of the function, and of course this is not a part of the function. And at x is equal to 1, so this is, and again, it's important to show that the function at x is equal to 1 is defined using this clause over here, which is this part over here. So this comes over here and becomes, at x is equal to 1, you will get basically this circle over here, and then at x is equal to 1, you will get a hollow circle over here. So this is basically the graph of your function. And you see that the function basically at x is equal to 1, the function is generating different values, essentially over here 0 and over here negative whatever that is, negative 2 at basically at these 2 points. So this point is negative 2. So then what that, as a result of that, the limit of the function at x is equal to 1 does not exist, because the function is generating this value 0 over here, negative 2 over here. They don't match basically. So although the function is defined at x is equal to 1, the limit of the function does not exist at that point. That is basically all about this function. These are interesting functions, and they are used in different situations. For example, in physics, there are some situations where you need to use, I think they are called piecewise functions or something like that. You need to use this kind of function in case, for example, the behavior of some phenomena or some phenomenon basically happens all of a sudden from some point in the domain of the function to some at some point basically the behavior of that phenomenon completely changes or something like that. Sometimes it happens, for example, in physics, in semiconductors, in many different places. This kind of thing is actually useful, and you can represent many sorts of phenomena using this kind of function. Okay. Now, the next thing that we have here is, let me check my answer here. Number 24 is the limit does not exist. Okay. Number 25. Number 25 is evaluate the limit of f of x. Limit of f of x at when x tends to 0, where f of x is equal to basically the absolute value of x over x for x is not equal to 0, and it's equal to 0 for x is equal to 0. So that means that the value of your function at x is equal to 0 is 0, and the value of your function at all x is not equal to 0 is basically this. Now this function is a little bit, well, of course, strange, or I would say weird even. Okay, so now basically I was trying to solve this problem and I did make a mistake. And well, now this function is basically something like this. Usually when you look at the graph of the function, you know what's going on with the limit. If you have understood the concept of the limit, of course, looking at the graph of the function, you know what the limit of the function is at any point on the domain of the function. So you know that the value of this function is 0 at x is equal to 0, this point over here. And this function is giving you, for example, let's say that at x is equal to 1, the function is going to be f of x is equal to basically the absolute value of 1 over 1, which is equal to 1. At x is equal to 2, then the value of the function is going to be f of x is equal to the absolute value of 2 over 2, which is equal to 1 again, and so on and so forth. So at x is at basically for all of these positive x's, the value of the function is going to be 1. This is f of x is equal to 1. But of course, over here, you know that this is not a part of the function, so you have to take that out. Now, when it comes to negative x's, the output of the function changes, goes to -1. Meaning that if you have x is equal to -1, then f of -1 is going to be basically the absolute value of -1 over -1, which is equal to 1 over -1, which is equal to -1. For x is equal to -2, you will get f of -2 is equal to the absolute value of -2 over 2, which is over -2, which is equal to 2 over -2, which is equal to -1, and so on and so forth. So then you will get this. So this is f of x is equal to -1. And of course, this point, you have to take this out. So you see that exactly around x is equal to 0, the function is giving you two different outputs, meaning that when x, meaning that the limit of f of x when x tends to 0 from the right is equal to 1, and the limit of f of x when x tends to 0 from the left is equal to -1. And so the limit of f of x when x tends to 0 from the right is not equal to the limit of f of x when x tends to 0 from the left. And therefore, the limit of f of x when x tends to 0, it does not exist. Does not exist. So this was using some graph, for example, but you can, of course, you can always do this using you can do it basically like this as well, meaning that, let me turn on this monitor over here. Okay, yes. Okay, so I need to put this thing on the other monitor so I can see what I'm doing. So now what you can basically, you see that the limit of f of x when x tends to 0 from the left, you can say that it's equal to the limit of basically this clause over here, the absolute value of x over x when x tends to 0 from the left, which is equal to the limit of basically negative x over x when x tends to 0 from the left. And the reason why I write the absolute value of x as negative x is that based on the definition of the absolute value of function, the absolute value of x is equal to x when x is greater than or equal to 0, and it's equal to negative x when x is less than 0, meaning that for negative x's then the absolute value of x is equal to negative x. So then, since over here the x's that we are examining are less than 0, then of course the absolute value of x becomes negative x, and so this gives me basically the value of the function at for those x's, meaning that it's going to be equal to the limit of, these two will cancel out, the limit of -1 when x tends to 0 from the left, which is equal to -1, which is basically this part over here. And you see basically how beautifully this limit is giving me the value of the function for all of these x's. Now, by the same logic, I can say that the limit of f of x when x tends to 0 from the right is equal to the limit of f of x, the limit of basically this clause, which is the absolute value of x over x when x tends to 0 from the right, and these are all positive x's. So this would be the limit of basically x over x when x tends to 0 from the right, which is equal to the limit of 1 when x tends to 0 from the right, which is equal to 1. So -1, +1. And so the limit of f of x when x tends to 0 from the left is not equal to the limit of f of x when x tends to 0 from the right, and so meaning that the limit of f of x when x tends to 0 does not exist. That's basically this exercise over here. Okay. Okay, so the next question is you want to find the limit of f of x when x tends to 5, where f of x is equal to the absolute value of x minus 5. Okay, so this is going to be the absolute value of x minus 5. That means that basically you're going to get something like, you're going to have a function like this. A function like this, but of course then you have to move it down 5 units, so 1, 2, 3, 4, and 5. So then you would get a function like this, and that's basically your function, right? And basically and of course at x is equal to 5, then you will get basically at x is equal to 5, I think your output is going to be 0. That means that the limit of this function is going to be 0 at that point. Number 26. Number 27 is 0, of course. So x is equal to 5 is basically this point over here, and of course as you approach basically 5 from the right or left, you're going to get basically if you calculate f of 5 here, that will give you basically the absolute value of 5 minus 5, which is equal to 0. So that's going to be 5 comma 0, and that must be basically this point over here, for example. This is 5 comma 0, and 5 comma 0 is basically this point. Now approaching 5 from the right or left, the function is tending towards this point, which is 5 comma 0, and so the limit of f of x as x tends to 5 is equal to 0. Or you can basically write it as the limit of f of x as x tends to 5 is equal to the limit of the absolute value of x minus 5 as x tends to 5, which is basically the value of the function at x is equal to 5, or f of 5 basically, which is the absolute value of 5 minus 5, which is equal to 0. That's basically that. Number 28, suppose that f of x is basically this function, a plus bx for x is less than 1 is equal to 4 for x is equal to 1, and it's equal to b minus ax for x greater than 1. Okay, so now if the limit of f of x at x is equal to the limit of f of x at x when x tends to 1 is equal to f of 1, what are the possible values of a and b? What are the possible values of a and b? Okay, so this function is basically at x is equal to 1, the output of the function is at 4. For x is less than 1, this is the output of the function. It's essentially a straight line, and with a positive, well, of course, assuming that, for example, a and b are positive, then with a positive slope, and then with negative slope over here for x is greater than 1. Now the limit of f of x when x tends to 1 is basically f of 1, which is equal to 4. The possible values for a and b are any a and b really. Of course, not any a and b, because the function has to be something like this. I mean, if the limit of f of x when x tends to 1 is equal to f of 1, which is equal to 4, then at 1, the output of the function is 1, 2, 3, and 4. So this is the output of the function at 1. Now, if I assume that a and b, for example, are positive values, then, for example, this is going to be some line with a positive slope. With a positive slope, meaning that if you have a line basically something like this, the slope of this line is 0, and the slope of this line is undefined. Now, if your line is basically, for example, something like this, the slope of this line is negative, and then the slope of this line is positive. So then this has to be some line with a positive slope, for example. Of course, I can assume that a and b are negative numbers, and then you would get a line with a negative slope over here, and on the other side you would get a line with a positive slope, because negative a then would be a positive number. Meaning that now and assuming that a and b are different numbers, so then I would get, for example, some line like this. But the important point is that these lines have this point of intersection at this point. The important thing is that these two lines have this point of intersection at this point. Other than that, they can have any sort of slope, and that would be fine. So then, based on this condition, we can calculate the values of the possible values of a and b. That's not a problem. Okay, so now what we can do is that if two lines have one point of intersection, suppose that you have, for example, some line like ax plus by plus c is equal to 0. Now, if two lines have one point of intersection, now suppose that, for example, you have a1x plus b1y plus c1 is equal to 0, and a2x plus b2y plus c2 is equal to 0. Suppose that these are basically two lines, and if we have these two lines, suppose that these are the two lines and they have this point of intersection. So what that means is that the point of intersection of the two lines, you can calculate it using, basically you can simply form a system of linear equations with two variables, and find the point of intersection. And the point of intersection would simply be basically, for example, suppose that I multiplied this by I divided this for example, call this equation number 1, call this equation number 2. I divide this by a2. I divide 2 by a2, divided by a2 to get it 1 over here. So I will get x plus b over a2 times y plus c. This is b2 actually, b2 over a2 plus c2 over a2 is equal to 0. And so then I multiply this by, call this number 3, and then 3 I multiply it by a1, so I will get a1x plus a1b2 by a2 times y plus a1c2 by a2 is equal to 0. Now if I write this equation number 1 over here, I can take x1 plus b1y plus c1 is equal to 0, and then if I subtract this from the other one, if I subtract this, I can cancel these two out, and there is basically a1b2 over a2 minus b1 times y is equal to a1c2 over a2 minus c1. And so this is equal to a1b2 minus a2b1 times y is equal to a2, and over here you have a1c2 minus a2c1, and so y is equal to this divided by this, or this times the reciprocal of this. So y is equal to this 1 times the reciprocal of this. So a1c2 minus a2c1 over a2 times the reciprocal of this. So this is times a2, and over here you have a1b2 minus a2b1. So this is your y. This is the coordinate of your y. And then if you do the same thing over here again, you can calculate the coordinates of your x as well. And this is of course the point of intersection, but I'm not really sure if that is the best way to solve this problem. There might be a better way. Well, the solution that I see over there is that x is equal to 1, well, you can of course then do the same thing and get the value of x as well, and then use basically the 2 points in order to find the values of a and b. But there is actually a simpler way to do the same thing, meaning that what you can do is that at this point at x is equal to 1, we know that the output of the function is 4. F of x is equal to 4. So and since these lines are supposed to basically intersect at this point, since this is the line number 1 and the line number 3, since 1 and 3 are supposed to intersect at 1, 4, then of course you can write, then 1, 4 is going to be a point on this line. So 1, 4 is a point on 1, which means that the line 1 would be basically y is equal to, for example, a plus bx, which means that y here is equal to of course this solution would have given you the answer, but it's a little bit, I mean, it's not really worth it to go through that much calculation to get to this simple point. So if y is equal to a plus bx, then y4 is equal to a plus b times 1, which is b. So that is one equation that you can use about on a and b, and then again the point 1, 4 is a point on this line as well, on line number 3, b minus ax. 1, 4 is a point on the line number 3. So, and the equation for that is y is equal to b minus ax. Is b minus ax. So then basically 4 is equal to b minus a. That is another relationship between a and b. And so now you can use these equations in a system of equations. A plus b is equal to 4, and negative a plus b is equal to 4. And if you add these together, you'll get 2b is equal to 8, or b is equal to 4. And if b is equal to 4, then a plus b is equal to 4. Then a plus 4 is equal to 4. Then that means that a is equal to 0. I suppose